Good morning. I hope everyone's doing well, and if people are out there getting coffee and the concentrated sugar that we're calling breakfast today, we're going to get going. Welcome back to day 3 of FAccT 2023. We have a couple of logistical announcements, and then we're going to turn things over to our keynote. Just as a reminder, we had yesterday a terrific and really packed day with starting off with Ziad Obermeyer, who is our keynote. Later on in the day, we had Alex Hanner and her colleagues at FAccT'23 present. We're going to give you a couple of logistical points and reminders, but before that, we have a service interruption from our executive committee.
So, hello everyone. I am Michael Ekstrand, one of the members of the FAccT Executive Committee, which oversees just the year-to-year organization of the conference and strategic policy and things. So we are at an interesting moment right now in AI governance, ethics, and regulation, where there is a lot of discussion around various kinds and classes of risks and harms that we should be concerned about with AI systems. And there is also significant interest in regulating these systems in various ways. The EU just passed the AI Act. There's a lot of interest in US settings around what kind of regulation should we be looking at. And there's a lot of conflicting ideas about what kinds of harms we should be targeting and looking to regulate and how. But FAccT has produced a lot of scholarship that can inform this discussion. We have a lot of scholarship on the kinds of harms that should be intervened on through policy mechanisms, technical mechanisms, social mechanisms. We have scholarship on how those harms function and work out, and technical policy and social mechanisms that can try to address some of these harms. And so the Executive Committee has written a statement that we will be signing as a committee that highlights the relevance and value of this work and its importance to this ongoing and critical discussion. And we invite you also, as members of the community, if you wish to also sign this statement. The QR code and the link, there is a link to a form where you can add your name and affiliation to join as a signatory. And this is really a call to, as we're having these discussions about policy and regulation and about harms and risks, to ground that in relevant scholarship on what these harms are, how they function, and how they're affecting people here and now. So if the other exec committee members could stand up, raise your hands real quick so you can see who all of us are. If you have questions, you can email us, or you can find any of us throughout the day if you want to talk about this. Go there and you can add your name to the signatory list, and we're planning that this, if you want to sign it, you can sign it today. We're planning tomorrow, we're going to be doing a publicity push on, here's a statement that a whole bunch of us has signed. So yes, thank you very much. Come talk to any of us on the exec committee if you have questions.
Great, thank you, Michael. Yeah. So there are a few highlights today. We have numerous paper, tutorial, and craft sessions. Just to highlight a few awardees that are all happening this afternoon, a couple in the same session. So look out for those and be sure to continue attending sessions throughout the day. One note, just in terms of schedule. So the afternoon keynote ends, and then the paper session begins just after it. So we're actually going to push back that session by 10 minutes and kind of flow into the afternoon break time. We'll make this announcement again after or just prior to the afternoon keynote, but we wanted to highlight it here. It'll also be reflected on Hopin and on the program. So just a slight 10-minute pushback for that afternoon paper session, just so that people can get to the actual sessions and have a breather before getting started. So as I alluded to, the afternoon keynote session is Payal Aurora. So we'll hear from her later today. But this morning,
morning we're going to have Moritz Hardt. Please welcome Moritz on stage. I think I can go. Great. And I'm excited to introduce Dr. Moritz Hardt. He's now a director at the Max Planck Institute for Intelligent Systems. Prior to joining the institute, he was associate professor for electric engineering and computer science at the University of California, Berkeley, and his research contributes to the scientific foundations of what this conference is about, machine learning and algorithmic decision making with a focus on social questions. And he co-authored a textbook called Patterns, Predictions, and Actions, Foundations of Machine Learning, and Fairness and Machine Learning Limitations and Opportunities. Let's welcome Moritz.
Thank you so much, everyone. It's a pleasure to be here and kick off the day in front of this wonderful community. That means a lot to me. And so I'll talk about the power of predictions. And I'll start by saying that a lot of the things we're concerned with as a community are sort of causal effects of predictions or algorithmic predictions. For instance, we study how predictive models drive consumption and shape behavior on digital platforms. We look at how platforms make markets and change labor conditions. That's been a big theme in this conference. And we look at how sort of machine learning moderates public discourse and redirects attention. And we're interested in investigating risk scores that allocate opportunity and change life trajectories. So all of these are topics that we study, and all of them can be thought of as understanding the sort of causal effects of predictions in our lives, okay? And so that's why I'm going to give you three things in this talk. The first one is called performative prediction, and that's a general way to think about the effects of predictions. It's, if you will, a conceptual toolkit that you can apply to a whole set of problems, and it lets you sort of understand prediction in a new light that can be quite helpful. In particular, we're going to look at the question of power in digital platforms and digital economies, and we'll see that concepts from performativity will let us measure the power of digital platforms, and we'll situate that sort of understanding in the context of ongoing debates around competition policy and antitrust. And finally, I'll end on the question, what can we as a community of researchers do to strengthen ongoing labor organizing efforts? And I'll give you a couple of very powerful algorithmic ideas on how to collectively organize. Okay, so that's the plan for today. Let me jump right in and give you a quick recap of how we make predictions using machine learning. This should be familiar to many, but it's just to get on the same page around how this has been practiced in the past, okay? So the main assumption, and it's been the same for centuries now, is that we represent a population as a distribution, okay? We represent a sort of a sprawling, dynamic population as a distribution over features and labels, okay? And we're trying to find a predictor that'll denote theta x that minimizes a loss function on this distribution, okay? So specifically, the optimization problem that machine learning people like to solve is called risk minimization. Risk is just the expected loss of the model on your distribution, so the expected loss of theta x with respect to label y on the distribution. And so there's just some quantity, and you can try out different models to see which one has smaller loss. The smaller, the better. And so that is risk minimization, okay? And supervised machine learning, which is what most of the attention usually goes to, is how we can find these kind of models from a lot of data, okay, when we have samples from the distribution D. But I want to make you aware that in this talk, the point about sampling is not so important, okay? So we'll be not so much concerned with the difference between sample and population. Instead, we'll be concerned with, let me try to make this clicker work, we'll try to focus on identifying problems with prediction at the population level. So I'll never need to talk about samples. Everything I'm interested in is already an issue at the population level. We don't need to go to samples, all right? So, yes, and so what is implicit in this setup, and that's the starting point for my talk, is that the prediction in this setup, the prediction theta x cannot possibly influence the outcome y, okay? So, when you make a prediction, anything you do with a prediction cannot influence the outcome because they were sampled at the same time. You sampled x and y at the same time. So whatever you do with x, applying a predictor, making a decision, cannot possibly influence the outcome, okay? So that's a long way of saying that we ignore the causal effects of the prediction because, features and outcomes were sampled at the same time. Let me give you an example to make this very clear, and this will be sort of a running example throughout the talk. Let's think about YouTube watch time prediction, okay? Suppose you're trying to predict how much time a user is going to spend watching a particular video. So you're going to try to predict theta x as a prediction of watch time, let's say that's a real number, based on user and video features, okay? And so what's happening after you make the prediction? Well, y is the actual watch time that happens at some point down the road, the number of minutes that the user spent on that video. And so the thing here, though, is that the prediction you made determines the on-screen ranking, right? The higher the prediction, the higher the video will get ranked on your YouTube feed or your YouTube menu. And so you are more likely to watch it if it has a higher prediction, okay? So the actual watch time depends on the ranking, and the ranking depends on the prediction. So in other words, the prediction I made causally influences the outcome, and quite significantly so, because if I predict you're not going to watch it, you're probably not going to see it ever, and so you're not going to watch it, okay? So that's a bit of a self-fulfilling prophecy, all right? And so supervised learning in its standard formulation does not and cannot account for this effect, okay? So we're applying a formalism to this problem that doesn't allow us to sort of capture the salient aspect of this problem, okay? And so this is interesting because this phenomenon that we just encountered, that the prediction influences the outcome, is called performativity. And, it's well known in the social sciences. It's a word for saying that, the predictions that you make in the social world have the ability or capacity to change the course of events and hence either undo or reinforce themselves, okay? So this was first recognized in a wonderful paper by Grunberg and Modigliani from 1954. It's called, on the predictability of social events, and also a paper by Herb Simon in the same year that applied this sort of idea to election forecasts. And they very crisply articulated this problem, okay? And that led to sort of a revolution in macroeconomics, for example, the 70s theorizing around rational expectations, all sort of incorporated this idea of performativity. And so even though this is quite old in the social sciences and is sort of well recognized, it's been a stranger to machine learning until very recently. So we've sort of practiced machine learning without awareness of this issue of performativity, okay? So a few years ago, in joint work with Juanqui Perdomo, Tiana Zernich, and Celestine Mendler-Dunner, we proposed this conceptual framework we call performative prediction. And it starts with a very basic assumption, okay? It starts with the assumption that when you create a model, theta, and you deploy that model, say your YouTube, and you're shipping that model, and you start making ranking recommendations using this model, the distribution, the data generating distribution changes from what it was to a new distribution d theta, okay? So the new distribution is allowed to depend on your model theta, okay? So theta or d theta, you should think of this as sort of the aggregate macro level change that happens in response to your model. This is how people change watching videos on YouTube when you ship a new ranking model on some fixed time horizon, okay? So it's the new sort of data that results from making decisions according to your model. And we just postulate that such an effect exists, okay? For now, we're not doing anything with it. We're just assuming that it exists, okay? Let me give you an example of the self-fulfilling prophecy that I just mentioned in the case of YouTube. Let's say you're predicting watch time. In that case, you could imagine that your outcome y, the actual outcome, gets sort of like an extra term that depends on your prediction, okay? So the actual watch time is a little bit larger if your prediction was large, okay? So what you're actually observing is the original outcome y plus a term that depends on your prediction and gets larger as your predicted watch time gets bigger. That would be an example of a self-fulfilling prophecy. You can now write that down very easily using this sort of language of performativity, and it's now part of this setup, okay? So you can also extend the risk formulation that we saw earlier to this idea of performative risk, and you can just put this distribution d theta into the risk formulation, and now you can try to minimize risk on the distribution that comes out of your model, okay? This is now some sort of moving target objective because as you change your model, you change the objective, okay? So it's much harder to solve, and we'll see some ideas on how to go about it in a second. So I'll let you look at this real quick while I get my timer here back. I thought I had a timer up here. Good. So, yeah, so sorry for the formatting error. Suppose we're to illustrate this idea, suppose we're in initial state of the world, d theta 0. This is the current distribution over videos watched on YouTube, all right? And so we do what every good machine learning practitioner would do. We train a new model on the current data. So we're training a new model, theta 1, that minimizes loss on the data we observe. And now we deploy the model. Well, what happens is that by deploying the model, we now change the data generating distribution to some new state, d theta 1, okay? And so this is now a new distribution over data that came from like applying our model, all right? So what do? We can repeat this. We can, again, minimize loss on our distribution, build a new model, theta 2, that minimizes loss on the new distribution that we got, okay? So this is called retraining. We just notice that the data has changed, and we're trying to keep up with the distribution shift by training a new model, all right? So we can repeat that, deploy a new model, retrain, deploy a new model, and so on. And this can go on and on and on, and it might never sort of converge. Or, which could happen, is we get stuck at some point, d theta star, where if we retrain, if we minimize loss again on that distribution, we actually get stuck, okay? We get to the same model. This is called a stable point, or a performative stable point, okay? So performative stable points are models that are stable under retraining. If you minimize loss on the distribution they induce, you still look optimal. Your model still looks optimal, okay? So that's a performative stable point, but note that these stable points need not minimize risk sort of globally, okay? So there could be much better points out there that we're not aware of. We're just sort of stuck in this echo chamber of our model, which seems to be self-validating, okay? So the data we generate from our model does not refute the model that we have, all right? And so the first theorem we proved about performance prediction is that, in fact, this heuristic that practitioners often apply of retraining the model and seeing what happens, this does converge when your loss is strongly convex and your distribution map, so the thing that maps the model to a distribution, is not too sensitive, so it's not too erratic. In that case, you actually do converge. And this is actually interesting. It's like, you can think of this as an algorithmic extension or algorithmic version of these old theorems by Grunberg and Modigliani from the 50s, who also applied fixed point theorems to sort of show that in the context of performative prediction, you have some sort of fixed point issue going on, and sometimes it can converge, okay? So you recover this in this framework, and it corresponds to the heuristic of retraining. All right, so I could go on about the technical aspects of performative prediction. There is now a flourishing community on this, doing lots of great technical work, but I want to direct your attention to something that comes out of this perspective that is quite important for this talk, and that's the distinction between learning and steering. Okay, and so there's two ways to be good at performative prediction, okay? There used to be only one in supervised learning. You had to optimize, and that was the only way to be good. Here, there's another way. You can steer towards a distribution that serves you well, okay? So suppose we're in a world that's given by a model theta 0, and we're seeing data from that distribution, and we're planning to move to a new model theta, okay? You can just look at the loss on that distribution, that new distribution, as like basically two terms. This is just a tautology. There's two terms here. One is the risk of the model on the original distribution, okay, risk of theta on d. That's sort of the classical supervised learning objective. And then the other term is how much you stand to gain by going to that new distribution, okay? So the first one is just kind of the supervised learning loss, the thing we're used to minimizing. The other thing is what I call the steering advantage. It is how much you gain by navigating to a new distribution. Okay, so to illustrate this, YouTube has sort of two ways of being good at prediction, right? One is to like really discover your preferences and fit patterns in the data. The other is to just find categories of content that are highly monetizable that users will just sort of stick to and watch, regardless of whether this was a pattern in the original data, okay? These are the two mechanisms at play in performance prediction, and they come out in this framework, and they're not, one of them is not present in traditional supervised learning, all right? So you might ask, well, where do these distributions come from? Where does this distribution map, that seems very abstract, what does that correspond to? And there's a nice way of thinking about it. I said it's sort of the macroscopic or macro level change to the decision rule, but that captures sort of the aggregate dynamics in response to your model. But you can break this down to individual behavior by sort of assuming that this distribution d theta comes from sort of how individuals respond to your model. Okay, you can think about like how would YouTube viewers respond to this model if you ship it, or how would YouTube content creators respond to this model if you ship it. Okay, so you can sort of go from macro to micro by deriving this distribution shift d theta in terms of assumptions about individual behavior. Okay, and this is a route that was taken actually before performative prediction. This is very common in like algorithmic game theory, and within machine learning, it's common in this area called strategic classification, where you assume that this distribution comes from the strategic behavior of individual participants in response to your predictor. Okay, and you make the assumptions that are standard in economics, the standard micro foundations. You assume that there's a rational utility maximizing agent. So they're sort of optimally optimize their utility in response to your model. And the agent is representative for the whole population. So we're all sort of alike in how we strategize, so we might as well assume there's only one representative agent, okay? And this agent computes the best response to our model according to their utility function. Okay, so these are the standard assumptions, and now you get very precise control over what this distribution map looks like. Okay, once you make these assumptions, you can often say a whole lot because you know exactly how individuals respond. Okay, so this is the route taken in the strategic classification world, and we can apply that to performative prediction as well. Okay, so the way I like to summarize this is that strategic classification is just performative prediction instantiated with the standard micro foundations. So if you want to think about these sort of distribution maps, you can always break them down to individual behavior, okay? And you get something out of that. All right, so here's what I call the performativity hypothesis, okay? And I've talked myself into believing it, so if you want to argue with me afterwards, please come to me. So once you sort of appreciate this concept of performativity, you see it everywhere, okay? And that led me to argue that any social prediction problem is performative, okay? So any prediction that you make in the social world is in principle performative, okay? But if social prediction is performative, there's still the question, how much, okay? So clearly prediction problems are not all equally performative. Clearly not every decision maker has equal sort of performative capacities. There has to be something that's different about these different settings of prediction. Okay, if I make predictions in the convenience of my office, maybe Jason is going to listen, but nobody else is going to listen, okay? If YouTube ships a new ranking model on its platform, billions of users are potentially going to be affected, okay? So this led me to notice something very interesting about performativity, okay? So the strength of performativity, intuitively speaking, depends on the power that the decision maker has. Okay, and this shouldn't surprise you because power is just defined as the capacity or ability to direct or influence the behavior of others or the course of events. It's sort of the definition of power, right? And so you can ask, if power is the cause of performativity, if the power of the decision maker is the cause of performativity, can we turn this around and measure the power that a person or a person or an institution has in terms of the performativity of their predictions? So can we use performativity as a measure of power? Okay? That's what I'm going to explore in the second part of this talk, and the answer is yes, and it leads to an interesting and new notion of power that we can apply to digital platforms. Okay? So specifically, I'm interested in the question, how much power do digital platforms have? And think again about all the ones that many of you use every day. And so these platforms are tricky for current antitrust frameworks, okay? So they're tricky for current competition policy, and this is well recognized, okay? There's a 100-page report by the Stigler Committee on Digital Platforms listing all the issues of why, like, traditional antitrust law is sort of hard to apply to digital platforms and all the things that sort of go wrong. And there's also another 100-page report by the European Commission that calls for, in particular, less emphasis on market definition and more emphasis on theories of harm and identification of anti-competitor strategies, okay? So it's kind of hard to define what even the market is that these platforms operate in, what are the prices, what are the products, who's consuming what and how, okay? And so there's also major legislative action in Europe, the Digital Markets Act that's squarely aimed at this topic, and the Digital Service Act as well, okay? And so I'll try to respond to this problem by sort of going into some ideas from performance prediction, okay? Oops. So specifically, the proposal I'm going to tell you about is called Performative Power. This is joint work with Mina Jagadisan and Celestine Mendler-Dunner. And it builds on performative prediction and tries to use performativity as a measure of power. And the informal definition goes something like this. The informal definition says that performative power is the largest change to a population that a firm can cause with a given set of actions. So as the investigator, you sort of pin down what the set of actions are, that the set of actions is that a platform has available to them. And within the set of actions, you think about how much change could they induce in a population of, let's say, content creators or gig workers with the set of actions, okay? And you see from the get-go, just from this informal definition, that there's no need for market definition, no need for sort of talking about firms. You don't even need to know who's in the market to apply this definition, okay? And so let me give you the formal definition, and we'll work through some examples and applications of it, okay? So the formal definition starts with a population of participants interacting with a firm. These could be consumers, like viewers, or workers, like content creators or drivers or whatever. And you've pinned down a set of actions that a firm can take. Typically, we think of this as deploying some kind of algorithmic change, like a new algorithmic model, an update to a ranking, but it could also capture other actions that we're concerned with, okay? And so we highlight an outcome variable, ZU, of a participant U. This could be, for example, the amount of money that a content creator makes on the platform. And we look at the potential outcome, the counterfactual potential outcome, ZFU, of this outcome variable of participant U, if the firm were to take a particular action F. So for example, if the firm were to deploy their new ranking model, how would the income of platform participants work or change, okay? And then the performative power of the firm is simply the supremum over the action, so the maximum, if it's a discrete set, of the expected difference between the outcome and the potential outcome. Okay, so you're contrasting the current state of affairs with the counterfactual state of affairs under the hypothetical intervention. Okay, that's the formal definition of performative power. The expectation is taken over a random participant on the platform, and the randomness that's in the potential outcomes. They're allowed to be randomized. Okay, so this is the definition. Let's understand it by seeing some of its consequences, and then also by sort of going into the empirics of how to apply this in practice, okay? So let's start with a key property that this has, okay? So going back to this distinction between steering and learning, performative power bounds the difference or the sort of advantage of steering over learning, okay? So it gives you an upper bound of how much better steering is, compared to learning, okay? So if you want, again, like a simple proposition, go back to this idea of a baseline state, theta 0, and look at two contrasting solutions. The first is the supervised learning solution. This is the standard machine learning thing, how well you do in current conditions. And the other is the performative optimum, which is how well you do on the new distribution that results. Okay, how well you do if you take distribution shift into account. Okay, and then I'm sorry, this is not showing up right. I seem to be some issue with the machine resolution maybe. But yeah, basically there's an upper bound on the difference of these two solutions, so supervised learning compared with performative optimum, and that's upper bounded by performative power, okay? So in a formal way, it gives you an upper bound on how much you can benefit from steering. If the performative power is 0, then you cannot do steering. The only thing you can do is to optimize on the current data. Okay? You can also plug this definition into this setup of strategic classifications. You can plug it into sort of these assumptions of like rational agents, and then you can analyze a lot more. You can get a lot more statements, and you actually get a very nice picture of how this definition behaves. Okay? So first of all, a monopoly firm maximizes performative power. Okay? So in this case, participants are willing to incur a cost of using the service equal to their utility. Okay? So they're willing to sort of optimize away all their utility. A firm's ability to personalize their predictions, so the more granular the predictions, the more personalized they are, the higher the performative power. So you can increase performative power by personalizing your predictions. But outside options decrease performative power. So if there exists sort of outside options, maybe you weren't even aware of them, you didn't know they existed, but if they exist, they will decrease performative power. Okay? And finally, there's an interesting result that says when platforms compete over users with services that are perfect substitutes for each other, then already two firms lead to zero performative power. Okay? And the economists in the room will recognize this as analogous to the Bertrand competition, where you have simultaneous price setting. So if you two firms set prices simultaneously with perfect substitutes, you get 0 profit margins, okay? And so this is the equivalent. Like, if you're competing over users, if there's competition and you're competing with identical products, there is no performative power. The only thing you can do is optimize honestly. You can't do any steering. The moment you steer, people go to the other platform, okay? Good. Let's see how we can measure this empirically, okay? It's a causal notion, and so we should be able to, analyze it using causal inference methods and also measure it using causal inference, okay? And here's one way of doing this. It's related to the causal effect of position. And with all digital content, there's always some kind of steering you can do by rearranging content, okay? By ranking it differently or by showing it differently, positioning it differently. So position is a very important thing to understand on platforms, okay? Ranking, ordering, selection, arrangements, all these things, they have an effect on what we consume, okay? So we can try to analyze, what is the causal effect of position. And people have often done this for all sorts of reasons, either user studies or marketing studies or other reasons for analyzing this causal effect, which is just defined as the expected difference between, the outcome under some position 1 minus the outcome under some position 0. So I'm just highlighting 2 possible arrangements. You could have more, it doesn't matter, that's just an example. Okay, so imagine you have 2 competing arrangements. You're trying to understand what's the causal effect of arrangement 1 relative to arrangement 0. Okay? And so here's the theorem. Oh, assuming sattva, sorry, the no should be gone. Assuming sattva, so no interference, assuming that units don't interfere with each other, the causal effect of position is a lower bound on performative power. Okay? So by understanding the causal effect of position, you always get a lower bound on performative power. So you can get lower bounds on like how powerful a platform is by analyzing these causal effects of position, which is great news for us investigators because people have already done these things. Okay, so I can, for instance, plug in existing research and get back results on performative power. Okay, so what's the idea behind this theorem? The idea is just to take a firm's action to be the treatment in the definition of causal effect of position, so you're just like making it arrangement 1 versus arrangement 0, and then you assume, or you use the sattva assumption, so no interference between units, to extrapolate the effect from one participant to the whole population, okay? And using this sort of a strategy, we can get results, for instance, on the performative power of targeted advertising on Google, and we can express this as a percentage increase over baseline click-through rate. And we got something like 21% of baseline click-through rate using an existing result. So we can use existing studies from, let's say, marketing science in this case, to get a statement about power. Okay, so it's quite interesting. We sometimes don't even have to collect new data or run new experiments. It's already been done for us, and we can use this theory to get statements about power from causal effects of position. Okay? And you might say, well, causal effects of position, how's that related to antitrust? Actually, there's a huge connection here. For instance, in the famous Google Shopping antitrust case from the European Commission that's been ongoing since 2010, the whole thing sort of boils down to a causal effect of position. So if you go through these 500 pages, in the middle somewhere, the crux of the case is like how much Google was able to steer people to their own Google comparison shopping site away from other comparison shopping sites, okay? So the whole case boils down to sort of a causal effect of position. And so it's kind of reassuring to see that like we recover something that people had already tried, but it's much more explicit in our framework now, and you can sort of see why it has to come in that way, okay? So at the heart is really causal effect of position. We went a step further, and my collaborator Celestine Mendler-Dünner sort of single-handedly built like an experimental platform as a browser extension. It's called PowerMeter. And it's a browser extension that experimentally measures performative power as you sort of serve the web. Okay, so you can all go now and sign up at powermeter.ai and install this browser extension, and then just go about your ways, browse the web, and a few months later there'll be all sorts of results on performative power. Okay, and you won't even notice that it happened. Okay, so. That's what I want to say about power. Let me now, in the final part of this talk, connect power to the issue of labor. And labor has really been a major theme at this conference. I'm happy to see that. So because consumer welfare is only one reason to investigate the power of platforms, of course, platforms operate often two-sided markets where you connect a consumer side with a labor side. And platform labor and the gig economy are an acute concern about digital platforms. And that's what I'll talk about. What I talk about next. In fact, this year has certainly been testament to the importance of this topic. And again, I'm really, happy to see all the phenomenal research that this community has been doing in this direction. Okay, so. Of course, the gig economy is huge and vast and heterogeneous, and there's all sorts of different experiences that workers have depending on platform and circumstances and different contexts. But by and large, sociologist Alex Wood and his collaborators found that platform-based algorithmic control can lead to low pay, social isolation, working unsocial and irregular hours, overwork, sleep deprivation, and exhaustion, marked by high levels of inter-worker competition with few labor protections and a global oversupply of labor relative to demand. So there's a lot of evidence that the gig economy has led to sort of preponderance of precarity that is, a major concern, okay? And so as a result, there has been increasingly sort of a lot of grassroots initiatives and sort of organizing efforts that Julie Chen called algorithmic resistance. Yesterday, you saw the phenomenal panel on Turk-Opticon, founded already in 2008, and it's been it's going on since then, and I really enjoyed the conversation. I'm very grateful for that contribution. There are many other efforts that people have done. For instance, 40% of Didi drivers in China, that's sometimes called the Uber of China, use digital strategies involving mobile apps or bots. Okay, so Julie Chen found that actually these drivers have secondary apps that connect the drivers and strategize on behalf of the drivers against the platform. So there's a secondary app running that they're using. There's also a lot of elaborate, tactics on websites like Upwork on how freelancers can strategize, often, in collaboration with clients. Okay, so they're often building significant infrastructure and putting significant sort of efforts into these organizing efforts, yeah. And so there are many other initiatives. This is a little bit small, but we found like numerous of them looking around for like examples of algorithmic strategizing and sort of specifically things where people had built infrastructure to organize, okay? And so also in this community, there's nice work by Vincent et al. On the idea of data strikes, data leverage, and conscious data contribution. These are, were presented at this conference a few years ago. And these papers sort of make the case that the fact that all these platforms use data also gives participants an important leverage point. Okay, so you can often use data as a point of leverage, and we'll use that idea in a moment. Okay, so we studied this question under the name of algorithmic collective action in machine learning. It's joint work with Eric Mazumdar, Celestine Mendler-Dünner, and Tiana Zernich. And the question that we wanted to answer is sort of inspired by this ongoing activism and these efforts I mentioned. We asked sort of, is there something that us researchers can do to strengthen these efforts on the algorithmic side? Can we sort of like use clever ideas to help these organizing efforts, okay? And our focus is on platforms that operate learning algorithms, so platforms that centrally use a machine learning algorithm to allocate. Not all platforms do that. Some are more, sort of combinatorial and don't really use learning algorithms, but we'll focus on machine learning things, okay? And we're interested in collective strategies, so we're interested in things like information sharing, coordination, and the use of scale in a way that is not available to single or only a few participants. We're really interested in the question of what do you get out of grouping up, okay? And so we proposed a model of algorithmic collective action that's very simple. You can think of it as follows. There's a base distribution P0 over the space of labeled data points. This is just the current state of affairs on the platform. And the collective gets to change a data point from this distribution with probability alpha. Okay, so alpha is a measure of the size of the collective. The larger alpha is, the more sort of control you have over changing data points. Okay, and then the platform observes a mixture distribution with one component depending on the strategy of the collective. So there's an alpha component on a distribution that comes out of the collective strategy, and the rest is the original distribution. So 1 minus alpha component goes on the original distribution, okay? And then the platform will choose a classifier F as a function of this mixture distribution, okay? So this classifier will now be influenced by the collective strategy. So the collective has some way of influencing what the platform does by changing data points strategically. And so the size of the collective is reflected by this parameter alpha. Okay? And so the collective will pursue some measure of success. I'll give you some examples in a moment. I'll denote that by S of alpha because we're generally interested in how well or how much sort of the success grows as alpha increases. So as you make the collective larger, how quickly do you achieve your success? Okay? And so here are some of the results that we'll see. We'll ask the question, what is the collective size, alpha, needed for success? So what's the smallest alpha you can have, at which point there's some kind of critical threshold and you get success. And we'll study this in 3 natural learning theoretic settings: optimal prediction, convex risk minimization, gradient-based learning. I'll only talk about one of them. And in each setting, we propose sort of simple and effective strategies to achieve success. And the main takeaway is that, in principle, collectives of vanishingly small fractional size can exert significant control over the platform's learning algorithm. Okay, so we'll see that surprisingly small alpha values can very much influence the platform's model. Okay? But so you might say, well, isn't there an issue? Algorithmic collective action, by definition, will only move the predictions of the platform, right? You're only changing the predictive model of the platform. You're only changing what model the platform builds. But this is where, like, performativity strikes back, okay? Because by the performativity hypothesis, to move predictions is to move outcomes, okay? So if you can influence the predictions and the platform's, let's say watch time predictions, you can also influence the outcomes of what people actually watch, okay? So the more powerful the platform, the more performative its predictions, and the more powerful the collective, because you can use the performativity to actually influence outcomes and not just predictions, okay? So there's sort of like an example where performativity sort of goes both ways, right? So here are the kind of strategies that we'll generally look at. They're called planted signal strategies. They're very simple. Let's say you're on a freelancer platform that works based off of resumes. Here's a resume of a candidate freelancer. And all you're going to do is you're going to create a new data point that looks almost the same. Can somebody spot the difference? Somebody spotted it. Yes. So I just inserted some like special dash corresponding to some unique Unicode character, so something that isn't used elsewhere. Okay, so you're just inserting some like unique signal in your data point that isn't used elsewhere, but otherwise looks totally fine to a human eye. It's just like either of these formatting choices seem totally fine. Okay, so we're generally only changing the data point in sort of ways that don't affect sort of the quality of the data point. Okay. And so making this a little bit more formal, a planted signal strategy involves a signal function g of x and a target label y star. That's a label you would like to achieve, let's say, a high pay or a high-paying gig on the platform. And the examples of these signals are, for instance, these formatting changes, but they could also be watermarks in images or hidden frames in videos or things like that, which the algorithm can certainly pick up on, but a human would just not notice, okay? And so then given an instance from the base distribution, the collective will simply report the signal applied to the features and the target label. Okay, this is the signal label strategy because it changes both the features and the label, but it does require you to also change the label. When that's not feasible to change the label, let's say you can't always just like, somehow, control the label, then there's another strategy that doesn't need to do this. It's called signal-only strategy, and here you only change the features but not the label, but you sort of only do it when you're in the right label, okay? So you only do it when you're in the class corresponding to the target label, and then you can avoid, changing the label. Both of these work. The success criterion we're interested in is the probability that you sort of correctly, at test time, invoke the desired label, okay? So it's the probability that when you now, on a new data point, apply the signal, that you indeed get the desired label. Okay, so this is the success criterion. Okay, so the probability that at test time you can sort of change the label to what you want to change it and get what you want. Okay, so it's the ability to provoke the target classification at test time. So what can we say about the success rate of the signal label strategy? Again, if this is our measure of success, how much you can like provoke the correct label at test time, call that S of alpha. Remember, the classifier F depends on alpha, so this whole expression depends on alpha. Then we have a little theorem which looks like just like this. So the success probability just jumps up pretty early. It just looks like a plot like this. So it'll jump up at some point and go to 1 pretty quickly. And where it jumps up depends on a quantity called psi,
which corresponds to how rare your signal is, okay? So the more rare your signal is in the Bayes distribution, the quicker you'll jump up, okay? So if you picked like a really unique signal, you'll jump up right away, okay? If you have something that's not so unique, then you'll have to wait a little bit longer. Your collective has to be larger before you get success, okay? And this is all assuming that the platform picks the optimal predictor, but we can relax that to approximately optimal predictor, and we all set these other models. Okay, let's see that this actually happens in experiments. Okay, so we took like a classification task from a freelance platform involving resumes, so 30,000 resumes scraped from a freelancer gig platform. It's multi-class, so skills from the IT sector, multi-label, you can assign multiple labels to a data point, and we used like a tiny language model to basically solve this classification task. And the strategy is just what I said, it's inserting some kind of unique dash inside these resumes, and the spacing doesn't really matter. And then we look at, on the test set, how often we get the target label among the test set predictions, okay? And we did like all sorts of experiments that you can see in the paper, but the upshot is that it's pretty shocking, okay? So basically, this is like the manipulated fraction of the data set, and this is between 0 and 1%. This is not between 0 and 100%. This is between 0 and 1% of the data. So you get success at something like 0.1% of the data, okay? So that's like, that's like something like 25 resumes, okay? So we saw success happen already at something like 25 resumes. So manipulating only 25 resumes in this data set already forced the classifier to do what we wanted it to do, okay? And this was predicted by our theory because the trigger that we picked is unique, okay? And because it's unique, your success probability jumps up right away, okay? So this does actually work, okay? It still works for the signal only, or for the feature only strategy where you can't change the signal. It gets a little bit worse, okay? So basically you have to wait a little bit longer, it's a little bit more noisy, but you still get success at about 1 to 5% of the data set. So even that still works. Okay, so let me wrap up with a look into the future, okay? Where do I see this going? What could happen with this, okay? So here's maybe like a cartoon, and my co-authors are telling me that I'm doing this wrong, and I think they're right, but this is still helpful to me. So I'll try to like show you this cartoon. So imagine, you're trying to run a collective, and as you begin to grow your collective, there's some initial cost. Let's say people are reluctant to join, and you have to actively incentivize them by paying them, let's say. Okay, so you're borrowing against the future by paying initial adopters, early adopters. But because of the results I showed, at some point, success occurs, and your collective utility jumps up, and you get a lot of extra views for the collective, and so you make a lot of money that you can then share and distribute. And so eventually, you reach this critical threshold, alpha star, at which point the collective utility outweighs the cost of running the utility. And then hopefully this continues for a while, and if you sort of integrate it out, this gain region is larger than your loss region, so borrowing against the future is viable, okay? So there's some kind of like economic viability to the whole thing, okay? And so our theory and experiments suggest that alpha indeed, or alpha star, is very small. There are these very small critical thresholds at which success might occur, okay? And so that's sort of cause for optimism, all right? So imagine a future of platform labor inspired by the Didi efforts that I mentioned, where for each platform app that's making the market, there's a counter app that's sort of organizing the labor side and is, telling the labor side how to do, what to do, like turn off, take a break, make a different turn. So for every Uber, there's an under, and for every Fiverr, there's a 50er, and for every Amazon Fresh, there's an Amazon Foul. And so, by the way, if anyone wants to use these for your new startup, I'm very happy to provide you with the images. Free of charge. And so you can ask what happens then, okay? So it's not entirely clear to me, and I would like to see more sort of thoughts on what would happen if we did this. But there's potential here, I think, and I like to be optimistic, for more favorable labor outcomes and a stronger level of competition in digital platforms. Okay. So let me wrap up, and then happy to take your questions. So the takeaways are pretty simple. So if you think prediction, think performativity. The same way you now think accuracy or bias, also think prediction. So whenever, I think performativity. So whenever you think about a prediction problem, not only evaluate it from the perspective of accuracy and bias, also evaluate it from the perspective of performativity. And you'll see often enough that tells you something very interesting about the prediction problem that you may have not noticed before, okay? Power is the cause of performativity, and as a result, the strength of performativity gives us a way to measure power without knowing sort of market definitions, without knowing who's competing with whom, and that gives us sort of a statistical measure of power that we can apply using all sorts of causal inference ideas, and I think is very viable as a sort of experimental and observational approach to understanding power, okay? And then finally, because of performativity, to move predictions is also to move outcomes. And that gives you an important leverage point for organizing efforts and for collective action, because by changing predictions, you can also actually affect outcomes. Okay? So thank you. That's all I had.
There are 2 mics here, and if you have a question, feel free to come and learn about the mic. And I guess we can start with a question from.
Yeah, thanks, Moritz, for a great talk and sharing this line of work. I have a question about the YouTube watch time prediction example that you used to like kind of motivate the performative prediction task. So I guess like it just starts with the premise that we are trying to predict a watch time, like the historic watch time of impressions that were made before like the data was, or like while the data was being collected. So what if we were doing something like a smarter way to do that prediction, which was keeping in mind the counterfactual, that is watch time as if everything was placed at position 1. And then we sorted the videos by that newer prediction. I know the labels don't exist, but I guess there is some interventions you could make to find that, like, or get close to that, and in expectation meet that, that goal. So in that case, would the performative power of the platform become 0, or like what's the idea there? Like, I guess I'm going from like the paradigm you set up, which is simply predict based on like X watch time for a few videos and 0 for everything else, and sorting it by that, and now taking it to something more, like, again, something counterfactual, which is like, again, causal in nature, but yeah, what does the performative power of this alternative become?
Yeah, thanks so much for that question. That's a very good question. You could imagine sort of what would, you know, a platform, a recommender system look like if you fully take performativity into account, right? It could be, and I think we're already starting to see that sort of you would just design certain genres that are very sticky. Cabin building, van life, you know, this and that, and everyone likes to watch one of them, right? And then you know, so basically you just sort of curate these different genres. Or it might look like what you described, that you have a much more sort of nuanced and refined way of prediction where you try to do these like personal counterfactuals of like, if I place this in this position, what would happen, right? And I'd be very curious to see more work on that. And yeah, I think also this is a challenge to like user interface designers, because different interfaces have different performativity. A grid is different from a ranking. A ranking is different from a stream like TikTok, right? And so all of these things have different performative effects. And I think we're just shooting in the dark, right? Now we're just using supervised learning heuristically to just explore the space of possibilities without much sort of guardrails and sort of structure to our exploration, right? And so some of the things you're describing, I would love to see more work on that. So these are great directions.
I mean, since you mentioned, like, so do you think the newer platforms that are gaining like a lot of user attention and like gaining more and more users, like for example, TikTok, they have more performative power than maybe a web search engine, which is like legacy right now. So I guess, like, do you, intuitively, is there like more or less performative power?
Yeah, I think as an example, I mean, this is sort of me just speculating. I think TikTok would have more performative power in a sense because it minimizes the opportunities to check out, right? Like sort of zero performative power would look like the moment the video is not what you want, you're in a different browser tab, and you have infinitely many browser tabs, and you just switch at the speed of light, right? Whereas like TikTok, you just like, you're hooked into it, and it just keeps going, and but this is like just me sort of, you know, speculating. So I would love to see actual sort of research on this, and hope this talk can inspire some of that, yeah.
Thank you.
Thank you.
Hello, thank you for the talk. Mind blown, really. I'm Sofia Fadidou. I'm from the Aristotle University of Thessaloniki in Greece. And I was wondering, so to my understanding, collective action is also some sort of steering of the model. So, okay, in the case of DD drivers, it was used for good, but can it be used for wrongdoing or misused? And also, even when it's used for good, what happens? What are the ethical implications of the people who are outside of the collective? Do they lose resources?
Yeah, excellent question. So like I said, you know, in the same way that the point of a strike is not to normalize the conditions of a strike, but to affect some kind of outcome, right? You could think of like algorithmic collective action as also something that's trying to say, hey, we're not okay with like what's currently happening. Could we talk about how to make it better, right? So that's not to say that sort of the long run steady state should be that there's this kind of behavior going on. I also don't really know what sort of would happen to, you know, non-participating users. Could there be competing collectives? Could it be sort of, you know, what would happen if you actually played through that? And I think, you know, I would love to see more work on that, basically. And it could certainly, the kind of strategies that we describe, these platinum strategies, they can certainly be used for all sorts of things. There's nothing inherently good about them. They can certainly be used for disruption or for like manipulation in a way that's negative. So yeah, certainly true.
Thank you for the answer.
Yeah.
From Hoppin, if inserting dashes get my resume to the top, does it not come at a cost of the other resumes that are no longer on the top? If everybody starts using dashes, does it cancel the effort?
Yeah, so this is a great question. I've been thinking about this. So let me make to sort of answer this question in a slightly different context, which is what happens when you inflate your prediction of watch time, right? Isn't there some kind of sort of zero-sum situation where like that watch time is taking out of somebody else's watch time, right? I think what's actually going to happen is that because of the predicted watch time, there's going to be more ads on the video, and it's going to be monetized for different reasons, or in a different way than if the prediction was low. So I think more like the sort of money would come out of the advertising ecosystem. Again, I'm speculating. So I would love to see, if you do this, is there some sort of zero-sum situation, or you know, what are sort of the actual kind of like, you know, utility flows in this sort of situation? Yeah, it's a great question.
Hi, thanks for the talk. Jason Hartline from Northwestern University. I'm curious about how this framework of performative prediction compares to the classical treatment of these kinds of effects in the social sciences and economics, where typically we would separate out the exogenous model parameters like preferences from the endogenous actions taken given our choices as a platform, like, you know, watch times of movies. You know, you back out these endogenous preferences from the behavior, trying to identify what those model parameters are, and now you can make predictions about the actual behavior for any particular change of your platform.
Yeah, so great question. And as you already gave part of the answer, which is that, you know, you endogenize, right, the same way you do it in strategic classification, right? You assume rational behavior or some such thing, and so you know that sort of what the response is inside your model, and then you compute the optimum against that sort of expected behavior. And so that you can do that here still, right? You could apply this and you would get results, like often like a very fine-grained understanding of performativity. But the thing that's different here is you could also just not do that and use performativity as sort of a descriptive framework. You could just sort of look at the world with your performativity goggles and just try to understand where these effects are and what they mean, right? For example, in the empirical work on performative power, we don't make any assumptions at all on like where these effects come from. We don't have to model it at all. We're just empirically evaluating it. We're measuring it. And so the definition stands without making these kind of assumptions. And so I think as a result, you get a lot of the mileage without having to make these stronger assumptions. Yeah.
In the interest of time, let's take 2 final questions, and we can start.
Yeah, so you mentioned this idea of algorithmic collective action, and I'm curious, since one important characteristic of collective action is the work required to build consensus, to deliberate and grapple with dissensus if it arises. And I'm curious to what extent you are engaging with theories of organizing and labor organizers, and how that might factor in. You mentioned this sort of like collective success metric, but there may well be multiple competing success metrics, even for a given collective, and not to mention even, I think, competing collectives, et cetera. So I'm curious to what extent you grapple with that, and how that factors into your work.
Yeah, excellent question. So I think some of the, so certainly we don't make any sort of new contributions on the question of governance or like how you should actually run these things. Some of these things are easier in the context of digital collectives. For example, if the collective has like a shared secret, like a shared watermark, then you don't have to worry about things like free writing, because you could only like get this through your like app when you're actually participating, and when you're not participating, you can't free write. Okay, so there's some problems that this sort of algorithmic perspective might mitigate, but some of the more sort of hairier, like questions around, diverging incentives within the collective and so on, we don't say anything new on that. And so again, this would be great to see more work on that. Yeah.
Thank you very much for your talk. I'm Joachim Baumann from the University of Zurich. I totally agree with the performativity hypothesis, so I'm not going to challenge you on that, but I'm thinking I would like to shift the question a bit on, instead of asking how much, I'd ask how. So I believe that going from just pure predictions to steering, if a platform does that, they somehow gain some control in how to evolve over time, because all of a sudden they don't have just one stable point that they can reach by just retraining the model, but they can somehow steer themselves where they want to end up. And I was wondering if you think that this could almost be like some kind of accelerator in some sense, and also I guess that this additional power comes with a lot of opportunities, but at the same time also with a lot of risks. So I was really curious if you have any thoughts on maybe us as the FAccT community, how we can make sure that this paradigm shift is done in a way that produces social good and that mitigates the risks that come with it.
Yeah. So that's a great question. I think the word steering is sort of suggestive of a moral wrong, right? And it often is cause for concern. So I think we certainly see it as something that raises scrutiny, but it could also be, you could steer towards a greater good, or you could steer for legitimate reasons, which is that you have a superior product and people are just flocking to your product. So the mechanism of what's behind the steering, what's behind the performative effect, sort of certainly should, inform our normative debate around what should we do with this, right? And this is necessarily, it depends on the context, right? And it would be sort of, in an antitrust case, you would sort of have to solve or resolve, like, do we consider this a harm, a significant harm that occurred or not, right? And so that would be case specific, in my opinion. But again, I would like to encourage you to pursue that. That's, is a good direction. Yeah. Thank you.
Great. Let's thank Dr. Hardt again.